expression in predicate logic, it is the case that I can rewrite it using only ands and nots. And I don't really need the or. How can I show that this is true? It's not hard. The only thing you need to do is how to figure out how to deal with the instances in which or appears. Why? Well, because we already know that those three are functionally complete. So if I have any expression, I already know how to rewrite it in terms of those three. Right? So let's give an example. Suppose I had to make this very concrete. So let's work with something with more variables so that it becomes a bit more interesting. Suppose I had an expression like this. Let's use three variables. This thing is not very well aligned. And I'm just going to fill this truth table with some values. Right? So we are going to have a function here, f, and I'm going to write it with, say, 3 ones in the truth table. So I just picked 3 rows to make one. Now, we are going to represent this in disjunctive normal form, DNF. And so this row here, so in DNF we are going to pick the ones, and we are going to write one term for each row that's 1 and make the or of them. So this here, this row is going to be represented as, let's write it in predicate logic, as not A, and not B, and C. This row here is going to be represented as A and not B and not C, and this one as not A and B and not C. And our finished expression in DNF will be an OR of those three, right? So we are going to have something like this, not A, not B and C, or not A and B and not C, or A and not B and not C. So this is a DNF expression for f, for this function f. And it only uses and or and not, like we know we can do. But suppose we didn't want to use or. Suppose we could not use or was not available, and we wanted to use it with only and not, right? Can we do it? Well, we have 2 ors here. We have to get rid of those ors if this is going to work. How can we do that? Well, we have to figure a way, and that's the basic trick, we have to figure a way of writing the or using only ands and nots. So, that's easy, actually. So suppose that we want to write x and y, and all x or y, and all we have to work with is an and not. Well, we can figure here that x or y is obviously the same, has the same truth table, is equivalent to not x or y, right? This is just trivial, right? I'm just using a double negation here. And then you can use the Morgan's law to realize that this part here, well, it's a negation of an or. What happens when you negate an or? It becomes an and, right? And that's exactly what we are going for. So this, when negated, well, the first negation just stays there, and this will become not x and not y, right? Because the negation of an or becomes an and of the negation of each of the terms inside. So, and exactly the same truth table as this thing here, not x and not y. So if I want to write an OR, I can always rewrite it like this. But, and that's something you should be careful about. Each of these terms here doesn't have to be a single variable, right? So if I have something very complicated or something else very complicated, I can also rewrite it like this. Right? It's just that I have to be careful to keep track of what x is and what y is, but this works even if x and y are not standalone variables, just like they are not standalone variables here. So we could use this, which we just derived, to eliminate or from any Boolean expression, from any expression in predicate logic, like this one. How? Well, let's look at this. We have two ORs here. Let's eliminate one at a time. So suppose we want to eliminate the first OR here. Then we look at the left, it's something, or we look at the right, something else. And so for this particular instance of OR, this is my x, and this is my y. Right? It's this or this. So if I want to eliminate the OR, I can just use this formula here, with x being this and y being this. And then I rewrite. Okay, the formula says that x or y is going to be exactly equivalent to what? To not x. What is x? This thing is x. So not a and not b and c, and not y. What is y? This longer thing here. So not a and b and not c, or a and not b and not c. Right? Okay, this closes here. This closes here. This closes here. So notice that the x here comes here, and the y here goes here. So this is x or y, and this is not x and not y, right? This is y and this is x. So we use this formula to eliminate this OR from this expression, but we still have an OR dangling here. How do we get rid of it? We use the same idea again. Well, the beginning of the expression doesn't need any fixing. It's going to be just the same, because it already uses only ands and nots. And then for this part, we're going to use the same trick again, only now we have x or y, and with x being this and y being this, right? So this is my x, this is my y now for this instance. So if I want to rewrite this, well, I'm going to use the formula again, and the formula is saying that this is equal to not x. What is x? Not a and b and not c. And not y. What is y? Y is this. A and not b and not c. Okay? And then I hope I'm closing the right number of parentheses. Am I? Let's see. This closes here, closes here. Probably closing one too many. In any case, so this is the result. We are done. This x is mapped into here. This y is mapped here, and we're done. This long convoluted expression here has exactly, precisely, the same truth table as this original one, but this only uses ands and nots. And using this formula, we can eliminate the or from any such expression and have, we could have started from any expression, right? Because an expression in D and F is always going to be an or of several things. We already know how to eliminate all or, so we could do this in any case. That proves that and or are enough to write any expression in predicate logic, right? You really don't need any other operator if you're going to express truth tables in predicate logic. If you're going to write functions, describe functions, all you technically need is those two. Of course, then the expressions become cumbersome and hard to read. So we do use more than just what's necessary in general for clarity and simplicity and length, but technically we didn't really need anything but and not. You could start from the DNF expression for any expression in predicate logic, which we know how to get, and then eliminate yours into ands and nots. So, the conclusion. This is a functionally complete set of operators. And this is also minimal in the sense that I can't remove more operators from that and still write any function. I can't write any function with just and. I can't write any function with just not. So this is minimal. This one is not minimal, right? Because I can still remove or.